Hello, my name is Minkyu Lee.
My name is Kush Patel.
Alright, we're gonna be talking about our robot, Team 9 robot. First, our task was estimating position and orientation, generating local map, global map, trajectory, generating the trajectory, avoiding obstacles, and robot's supposed to navigate waypoints with an accuracy of 3 inches. And robots should be able to return to the position in 14 minutes. Not in 14 minutes, but while updating the map. So what I'm gonna first talk about is odometry. How we use odometry to know where the robot is and to know what's the orientation of it. So as we learned in the class, within the wheel speed and within the within the encoders, we were able to figure out odometry function from the lab 1. We use odometry to incorporate to where's the robot and to return its position within the GUI. So every now with we use cosine and sine within the how much wheel was turned to return the position in the GUI. So that's how we figure out where's the robot, and robot color is printed with the purple if you look at the GUI. Next, we're gonna be talking about generating the local map.
The local map, we use an IR sensor, which is mounted on the front of the robot. What it does, it'll sweep from 90 to 90 degrees from the initial sweeps, and that'll scan pretty much every wall surrounding its front and back. Given that the angle of the IR sensor from the turret, we have an encoder that tells us, because it's a servo motor, we know the exact angle of the encoder. That way we can also figure out the exact location of the wall given the distance that the IR sensor returns, and that will determine the location of obstacles and walls, and then we can update that to the global map.
Alright, I'm gonna talk about how do they update to the global map. So we got local map position, we know distance from the, we know wall is how far is the wall from the robot and what's the angle. And now, because from the odometry we know what's the orientation of the robot and we know what is the position of the robot. Within those combined together, we can update wall location and global map. We also use a line mapping, and I also ended up dividing the line. If the 2 points are too further away from each other, I make them divide each line. So when it doesn't cover up the blank space, when there's a blank space, you recognize the blank space and it doesn't add anything else. I also add the correction function, so when it assume it wrong and when it update wrong, when it scans again, if there's a blank space, then it will update as a blank space again. Next, we're gonna talk about the trajectory, which is wavefront function.
So we implemented the wavefront algorithm to be able to navigate to the designated location we wanted. The task required us to move to the final goal using 5 waypoints. So pretty much we would update wavefront every time we scan and sweep, and the wavefront would go from the starting location to the waypoint, and then every time it updates, the current location would become the starting location, and it would use the current location to then navigate to the goal location. And wavefront pretty much works as in it designates the goal value as 1, and it increases the values around it, and then goes to the next point and increases the values around it, and pretty much continues on to the current location of the robot. That way the robot just takes a step into a square with a smaller value, and thus it has moved closer to the target. And wavefront was very effective and efficient in reaching the destinations of our waypoints.
Alright, next I'm gonna talk about avoiding obstacles. So our robot has capability of avoiding obstacle. When it sees the obstacle, you can see in one of the video in the computer, it's showing the computer vision. So when it sees the obstacle, it kind of treat as same as wall, so it won't go within the wall. We also have configuration space, so whenever it occupies, when the wall is occupying the grid, we also make them occupied that 4 grid connecting to that grid, so we don't go configuration space. We consider the configuration space of getting through that blank space. So within that 2 function, we were able to detect wall. We were able to detect obstacles, and we can avoid obstacle while we are heading to next waypoint or going back to home position. we also we have what we have is called escape function. So when it get blocked off, when it realize there's some obstacle blocking off the path within, like, that's what they think. When the, like, for example, when because of our line mapping, it block off all the path and it can't go anywhere, it got stuck in the same position forever loop, then it's gonna have one of the escape function. If that basically, if it I put I if it's in the same while loop for a long time, what's gonna happen is it's gonna sweep around 360 degrees and it's gonna update and correct that blank space. So, and after the correcting that blank space, and if it realizes there's a blank space, and it's gonna update to the GUI, and it's gonna tell the robot to run the wavefront again, then we can go follow that path again. Alright.
The robot, our robot overall, we were able to implement the wavefront, the mapping, and everything very effectively. We were able to reach all the waypoints within an accuracy of a couple inches. Sometimes it would be much closer. We would almost nail the exact location of it, and we did this all within about 11 minutes. After getting to the final location, our robot switches to the return map. Pretty much the task was that the obstacles could change, or the path could change, or the path just may not be the most fit path to return to the starting location, and thus it'll just reset to a return map, which then it would sweep and update the entire map around it, and it would go back. The return function took a slightly bit longer, a 14-minute time, but it was very effective in also also mapping the entire map, as well as avoiding all the obstacles and reaching the destination.
Alright. So I'm gonna talk about what was the difference between actual robot and virtual robot. Well, virtual robot, you think it's a perfect world, so odometry works perfect and IR sensor work perfect. But when it comes of real world, IR sensor give you the one of the glitch. It has sudden up, sudden distance, sudden like distance gets shorter suddenly, and sometimes distance suddenly get bigger, and so there's because of that glitch we need to add a filter. And for the filter, we use heavy averaging. If you are interested, we did it the final presentation. I believe there's a final presentation video. It explains more effectively in that video. Also, we use for the actual robot, because of this filter, we need to have more datas. So we make it 2-degree detection instead of 10-degree detection we use it in the virtual robot. Also, another thing about actual robot is because the wheel is not steady or stable. Because of that reason, we needed to adjust robot's orientation slightly, because sometimes it turned 110 degrees when we asked them to turn 90 degrees, and odometry think they turn only 90 degrees. The reason is one of the wheel was loose, so it doesn't turn as much as other wheel when it's supposed to. So that was the reason our odometry does not 100% replicate its actual location with an actual robot. However, if you just tweak that angle a little bit, it should be perfect. That's what we had, and yes. So I think that was our presentation. We were able to finish everything. We were able to navigate waypoints within 3" within 11 minutes. We can return to the position in 14 minutes within the 5" within 5 centimeter from the actual starting point, within slight adjustments. Adjustment. There we go.
I am a robot and I'm proud because I
thanks for listening and watching our video. This is Minkyu Lee,
This is Kush Patel.
and this was our RBE 3002 final project.